In 1901, a group of sponge divers were working off the coast of a small Greek island when they found something that shouldn't have made sense. Buried in a shipwreck, corroded by 2,000 years underwater, was a lump of bronze covered in gears, not decorative, not simple, a dense, interlocking system of over 30 gear wheels packed into a box roughly the size of a shoebox. For context, nothing built with this level of mechanical complexity shows up again in the historical record for well over 1,000 years. This is the Antikythera mechanism, and depending on which team of researchers you ask right now in the present day, it's either one of the most sophisticated scientific instruments the ancient world ever produced, or it's a fragile, unreliable toy that jammed almost every time someone tried to use it. Here's the strange part. Both of those conclusions come from serious, credentialed scientists. Both were published recently, and they directly contradict each other. Let's start with what everyone agrees on.
The device was pulled from a Roman-era shipwreck near the island of Antikythera, dated to somewhere around the 1st century BC. What survived is only about a third of the original object, 82 corroded fragments, including those 30-plus gears. For decades after its discovery, researchers weren't even sure what they were looking at. Early theories ranged from an astronomical clock to, more skeptically, some kind of elaborate decoration. It wasn't until 1974, when researchers used X-ray and gamma-ray imaging to peer inside the corroded fragments, that the true complexity started to become clear. Hidden inside that ancient bronze was a hand-cranked mechanical model of the solar system. Turn a small handle, and the device would move dials showing the position of the sun, the moon, and several planets. It could predict eclipses. It tracked lunar phases. For a machine built without electricity, without steel, without any of the tools we'd consider essential for precision engineering, that level of function seemed almost impossible.
Nothing else like it exists from the ancient world. Nothing close to it shows up again until medieval Europe started building astronomical clocks more than 1,000 years later. So the question everyone wanted answered was simple. How precise was this thing really? That question got a serious upgrade in 2024 when a team at the University of Glasgow decided to bring in tools that had nothing to do with archaeology. The mechanism includes something called a calendar ring, a circular band that would have been lined with evenly spaced holes, one for each day being tracked. The problem is that the surviving fragment of this ring is broken and incomplete. Nobody could say for certain exactly how many holes it originally had, which made it impossible to know precisely what calendar system the device was built to follow. Researchers Graham Wone and Joseph Bailey had an unusual idea. They applied statistical techniques originally developed to detect gravitational waves, the same kind of analysis used by observatories built to catch ripples in space-time from colliding black holes.
Using those methods on the surviving hole positions, they concluded the ring most likely contained between 354 and 355 holes. That number isn't random. It's almost an exact match for a lunar calendar year, not the solar calendar many researchers had assumed. In other words, cutting-edge physics built for the largest cosmic events in the universe helped answer a very specific, very human question about how ancient Greeks tracked the moon. The precision required to place that many holes at that spacing, by hand, in bronze, without modern measuring tools is difficult to overstate. Some of the holes were spaced with a margin of error smaller than the width of a human hair. That's the case for the Antikythera mechanism as a masterpiece. Then, in April 2025, a completely different team came along and complicated the story. Two engineers in Argentina, Esteban Seguetti and Gustavo Arenas, built a computer simulation of the mechanism's gear system. But instead of modeling it in its idealized, perfect form the way most previous reconstructions had, they built in something the earlier models tended to smooth over. The mechanism's gear teeth aren't perfectly shaped. They're triangular and slightly irregular, the natural result of being hand-cut 2,000 years ago rather than machined by computer.
When they ran the simulation incorporating those imperfections, the results were unexpected. According to their model, the mechanism could only be reliably cranked forward about 4 months into the future, before something inside it would jam or the gears would simply disengage. At that point, whoever was operating it would essentially have had to stop and reset the entire device, the ancient equivalent of restarting a printer that's stuck mid-page.
Their conclusion was blunt. Rather than a precise scientific tool used for serious astronomical work, the mechanism may have functioned more like an expensive, intricate novelty. Something built to demonstrate wealth, craftsmanship, and knowledge of the cosmos, sure, but not something a working astronomer could actually rely on for accurate day-to-day predictions. So, which is it? Here's the part that should genuinely sit with you. We're not talking about a disagreement from 100 years ago that's since been resolved. Both of these findings are recent. Both come from legitimate, peer-reviewed, or rigorously modeled research. And they point in almost opposite directions. One says this device was engineered with jaw-dropping precision. The other says it barely worked at all. It's possible both are true, just applied to different parts of the mechanism. The calendar ring spacing might reflect genuine mathematical sophistication in the design, while the gear train that actually moved the dials may have been let down by the practical limits of ancient manufacturing. Brilliant on paper, unreliable in bronze.
It's also possible we're simply looking at a single surviving example of something that once existed in a range of quality. The ancient equivalent of comparing one glitchy prototype to whatever polished, fully functioning versions might have existed elsewhere and simply never survived 2,000 years underwater. We may never fully know because we're not working from a complete object. We're working from 82 corroded fragments of something that was clearly the product of extraordinary ambition, pieced together by researchers using tools its original makers couldn't have possibly imagined, from gravitational wave detectors to computer simulations. And that's really the deeper story here. This device has been sitting in a museum case, mostly intact, for over a century, and we are still actively discovering new things about it right now, using science that didn't exist when it was pulled from the sea. The mystery isn't ancient history frozen in place. It's still unfolding in real time, with researchers on opposite sides of the world publishing conclusions that don't yet agree. Whatever the ancient Greeks who built this actually intended it to do, they built something so far ahead of anything else from their era that it took modern civilization more than 1,000 years to build anything comparable again. Whether it worked perfectly or jammed every few months hardly changes that. Somebody, in a workshop we'll probably never identify, looked at the movement of the sun, the moon, and the planets, and decided they could build a machine small enough to hold in 2 hands that modeled the entire visible universe. That ambition survived 2,000 years at the bottom of the sea. The full truth about how well it actually worked might still be waiting to be found. Thank you for watching all the way to the end. If this made you think differently about something you thought you already understood, that's exactly what this channel is for. If you have a request for any historical topic about lost knowledge, feel free to drop it in the comments below. Subscribe to Vanished Knowledge, and I'll see you in the next one.